All right. Today we are talking about the scientific method. And, this is one of those revolutionary things that changed our world. When people started really thinking about how is it that we can, come up with new ideas, new information through a testing process instead of just a thinking process. There's always been people throughout history that have done tiny little experiments in order to discover things. But there was a big period of our time when the idea was just to think about a problem. And we didn't really have this idea that we should go through a process by which to discover truth with testing and observation. So what we're going to talk about today is that method that we use now. And this method was developed, through the centuries, but really kind of kicked in, in the era from the 1600s and on, started becoming more and more common. And it is what has allowed us to advance scientifically much more today than we would have. So we're going to talk about scientific method a little bit today. And I think, I hope you have a great appreciation for this method of discovery, because this is what is useful to you in a day-to-day life, because you can use the scientific method to discover truth in your own life all the time. All right. So let's get going here today and talk about scientific method. All right, so our objectives here today. We want to describe how scientists construct hypotheses, describe purpose and features of a hypothesis, explain the purpose and methods of controlling conditions in an experiment, and then we're going to talk about the difference between theory, hypothesis, and law. A lot of times we have a misconstrued understanding of that, and so I really want you to pay attention to when we're talking about that, as far as what you may have thought before is not the case. It's kind of been ingrained in a lot of our, culture. It's not exactly the way it is best described. So let's go on to the next one. All right, so these are our criteria. So by the time we're done, I want you to be able to generalize a testable statement or a research question if I give you a set of data. And then I want you to tell me the differences between those different things, hypotheses, theories, and laws, and give examples of each. And I want you to be able to identify independent and dependent variables and controlled variables in an experiment and also on a graph. And then I want you to identify control groups in an experiment, and then tell me the difference between a control group and controlled variables or constants, because those aren't quite the same thing, but a lot of times students get those confused. All right, so let's start with the scientific method. We have somebody like Galileo. There were also some other scientists before him that were doing these experimentations, but he is one of the early figures that's known to use observation and experimentation. You might think about him dropping weights off of the Tower of Pisa. That was one of his experiments. He helped come up with ways of experimenting, right? Observing, experimenting, analyzing, that we now call the scientific method. Another scientist by the name of Bacon, who was also a monk, helped come up with some of these things originally as well and wrote them down. So there are lots of different scientific methods. And for me, I really want you to think about the idea that the scientific method is a way to solve a problem, okay? Study a problem or solve a problem. I don't want you to think of the scientific method as a series of steps. Now, there's a lot of steps that you'll see here. We're going to look at some steps. And yeah, you could talk about the different steps of the scientific method, but I don't want you to think of it as a series of steps. I want you to think of it as a way to solve a problem, okay? So when we're talking about the scientific method, don't say, oh, it's a series of steps. And we'll show you why. It's a way to solve a problem, a way to study a problem. Okay. So, and it's in an organized way. Went backwards. And boom. Let's look at this particular model. There's lots of different models, but for the most part, they're very similar. They start with observing, okay? Then you're taking a guess as to what you would think would happen. And you should have a reason for that, right? There should be something like either prior knowledge or some sort of observational information or data that's making you guess of what you think is going to happen. And then you go through and you'll test to see if that hypothesis is true. Remember, this hypothesis must be testable. Okay? Then you might find out, oops, that data did not support the hypothesis. So now you have to reject the hypothesis and come up with a new one. And this is one of the reasons why it's not okay to talk about the scientific method as a series of steps, because there are lots of little loops that happen in here. And those loops basically mean it's not like 1, 2, 3, 4 that you can follow. You've got, a process or a way of thinking. Okay, so let's say your testing is showing something that's true, that your hypothesis is true. Well, then maybe you're going to be able to come up with some models. You're going to be able to predict and try to see if it's true over and over and over again. You might be able to come up with a theory as to something that's happening. And then you're going to publish your results, all right? Well, maybe you're not going to publish, but you're going to share those results, right? You're going to put that out in the scientific community so that people can know about it. And now other scientists are going to be able to say, oh, that's really happening? Well, let me check it out and let me see if it's true for me as well. And, this is important because there are plenty of times in our history when people have made statements that aren't true, okay? And, even right now in our time where we have, all the different data that's coming out with the COVID, diseases that people are having, right? There's so much different information out there that it takes a while. For instance, when my father-in-law was, getting sicker and sicker, one of the things that was suggested was, what particular drug, and, there's anecdotal evidence, this drug was working for this doctor for these 3 patients. Does that mean it's going to work with a lot of them? Well, in the scientific community, scientists typically want to be conservative in terms of making statements. They don't want to say that this drug is going to work for everybody if it works for 3 people. And so a scientist wants to get a lot of data. They want to go through that loop and iterate that loop over and over again and repeat tests with different scientists in different situations, hopefully with the same criteria though. And once you get a bunch of those trials and they're all showing something true, then that is something that scientists like to get behind. Okay, because scientists don't ever want to use the word prove. They don't really actually, think that that's a word that they should be using. So it's important to keep in mind that as a scientist, you want to have good, solid data to support. And anecdotal evidence or a few different people, that's something important to look at and maybe to create a hypothesis out of and create an experiment out of. But it's not necessarily something that would make you proclaim to the world that, this particular drug is going to do, some amazing thing. Because then if you say that, you put your name on the line with that particular drug, and then they actually accept that, and people are trying it, and now people are dying because, you didn't know about one particular part of it. It's really important to have repeated experimentation. So for my father-in-law, there was one particular drug that Oxford had done a study on, and that study had shown that, there were people that were improving. A third of people, were not dying that would have normally. So it was cutting deaths by about a third. And so, my father-in-law was able to have that treatment. It didn't end up, changing his situation. But, there was data that was supporting that, and the doctors were willing to go for that. And you might be wondering, why is it that doctors won't try this and that and the other? This person does that drug and that person does that drug. Why aren't the doctors all jumping on? Some doctors are, some doctors aren't. Some doctors definitely have different standards by which they're trying to go forward with, data. And some doctors are a little bit more willing to take those chances. Maybe it'll work and I'm willing to just give it a shot. Other doctors are like, no, let's be more conservative. So part of that is personality, but scientists definitely want to have something proven. There was a group of scientists that thought that they had discovered cold fusion. And they had this experiment that worked and it was amazing. And they immediately published their data after one trial. Nobody else was able to replicate that trial. And those 2 scientists became completely disreputable in the scientific community. Basically, everybody thought that they had made it up and it was a hoax. Well, those scientists may have been telling the truth and it may have worked for some crazy reason that they weren't able to replicate. Nobody else was able to replicate it. So scientists typically have to be a little more conservative about what they say because their reputation, their professional careers are on the line if they make a statement. Anyway, that's going off on a bunny trail, but that's real life, right? It's kind of fun to get real life involved. And that's why we're talking about the scientific method, because it is about, where we meet the real world in a real situation, okay? All right, so let's continue going on. That was observing. So we talk about that first step, observing. Now, there's a couple different ways we can observe. We can observe through qualitative data and we can observe through quantitative data. Now, qualitative data is going to be non-numerical data. These are the things you're going to collect with your senses. Sight, smell, the taste. Hopefully you're not tasting any chemicals, touch, that kind of stuff, right? So that's qualitative. It's the quality of something. Now the quantity, if you're thinking of quantity, you're thinking of money, right? Or some sort of number. And so numerical data, and it should include a unit, right? So 5 is not a quantity, okay? 5 is a number. Quantitative data has the number and it also has the unit. So 27.5 grams, 19 cows, -8 Celsius. These are examples of quantitative data. So think of quantity. Another thing that we want to think about when we're thinking about observation is we want to think about the system that we're observing. Because you have to remember that in any observational environment that you have a system. My system might be this classroom and I'm doing an experiment in just this classroom. Maybe it's in a little test tube. Maybe it's in a cage. Maybe it's a lake, something like that. A system is going to be a specific portion of matter or area in a given region of space, right, that has been selected for study during an experiment or observation. And so systems are important to think about when we're talking about observations because you might see something happening in the system in one way, and it might not happen that way outside of that system. Okay, and that's one of the things that we're discovering, for instance, even with gravity, right? And so Newton makes these observations about the system and how gravity works on this planet. But does that work outside that system, right? Does that change when you get into different situations as you get close to a black hole? Does gravity work in the same way that Newton understood it, right? So system matters, and so you have to pay attention to the system. Oh, still going backwards. Let's go forward. Moving forward, moving onward. All right, so the hypotheses, right? So we want to talk about a hypothesis and what that is. So your hypothesis should be based on background knowledge or preliminary data. Okay, it's a generalized statement. But when you state your hypothesis, we always want your hypothesis to have some sort of because. Okay, we don't want it to just be, I'm making this crazy statement. It should be based on preliminary data or background knowledge. So have a reason for why you're guessing what you're guessing. And so once we use those generalizations, we've got to make sure that they are testable. Okay, we talk about, what's a testable hypothesis. So if I say something that kind of sounds absurd, I might be like, the moon is made of cheese. Well, is that a testable hypothesis? Yeah, I mean, maybe I'm not going to go to the moon, right? But somebody could get to the moon. And so the moon is made of cheese is a testable hypothesis, okay? However, if I said the stars are made up of the lost teeth of children, okay, is that testable? Well, okay, can I get to a star? Well, not at this point. Maybe, in many thousands of years, we'll be able to get to other stars beside the sun to do this observation. But wait a second. What kind of teeth? Lost teeth? Can I even find lost teeth in order to do an observation with a lost tooth to see that it turns into a star? No. Lost teeth are lost. So there's no way I can test a statement like that. So the statements might sound absurd, but if they are testable, then they are still valid hypotheses as long as they're based upon some sort of prior knowledge. Now, if I think that the moon is made of cheese, what prior knowledge do I actually have? Maybe that's not a good hypothesis unless I tasted some of the moon before, yum, 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 the moon is so yummy. All right, now, hypotheses are oftentimes put into if-then statements. Again, the then and the if. Okay, if such and such, then such and such. The if is the reasoning, right? The if is the background knowledge, the preliminary data, and then the then is what you think is going to happen. Okay. All right. Now we go on to testing. So for testing hypothesis, remember that we have to have experimentation that gives us data, and then you have to remember that it is okay to reject your hypothesis. As a scientist, you don't care if your hypothesis is true or not. It doesn't matter. You are fine if you were wrong. You had a guess, you do your experiment, and you're fine if you're wrong. And that's important to remember about a good scientist and a hypothesis, okay? You don't want to be biased. You don't want to be like, oh, I want my hypothesis to be true. Because when you are skewed and when you are biased toward hoping for an answer, then sometimes you interpret that data in an incorrect way. And that's what we do a lot of times. Again, kind of talking about, the COVID environment, right? I mean, masks versus not masks. Some people have a hypothesis of this. Some people have a hypothesis of that. And those two groups of people, the masks and the not mask people, they both have different biases. And so they look at the data and they interpret it in order to try to show what they want to see. Okay, both groups are trying to do that. Now, there is a truth, and that's the whole thing about science, is that we are trying to push to find the truth. And we want to collect information about the world around us in order to find the truth. So how do we do it in such a way where we can eliminate our bias and see what's actually happening? And that's difficult. And that's why science is so important. Science is so important, and why scientists have a really important job. And why, if they're doing their job, we have to really respect what they're saying. Because scientists aren't just going all willy-nilly at it. They are trying to take a very measured approach. And hopefully, nobody can eliminate bias, but hopefully scientists are trying to eliminate their bias so that they can be objective about their answers. Okay? All right, so that's why it's good to focus in and trust a little bit some scientists out there. All right, not going backwards, going forward. Where are we at? Nope. Maybe I do need to go backwards a bit here. Hang on a second. And going back. Okay. All right. No, so we did get that. All right. So we were at testing our hypothesis, and we're going to do an experimental design thing probably in class if we're going to do it. So we're going to skip through that right now. Let's talk about our experimental design basics. And again, some of this is review, right? An independent variable versus a dependent variable. Remember, the independent variable is one that you control the measuring of, okay? It's what is being manipulated. It's the reason for your experiment. A lot of times this is going to be your experimental variable. But the independent variable is what you have the ability to control. So for instance, time, in a lot of experiments, time might be your independent variable. Maybe you're seeing what's going to happen over time. Now, you aren't actually controlling time, but you're controlling the measurement of it. I'm going to measure it this often, this often, this often, and see what the changes are. And so that's why that's the independent variable, because you control the measurement of it. The dependent variable is what's changing based upon the independent variable. And so what you're going to see is that dependent is going to depend upon the independent variable. Okay, so that's how you remember that. Dependent depends on the independent. And that's going to be the thing that we end up measuring. So maybe if I were doing, how much is this plant growing over time, then the height of the plant might be my dependent variable. Time would be my independent variable. Now, there is something called a control, and there are things called controlled variables or constants. These constants are things that we try to make sure they stay the same in our experiment every single time. Okay? And so these are our controlled variables, like what's the temperature of this room when we're doing the experiment? What's the pressure of it? What's the humidity of it? We want to try to keep all those things the same so that those different little variables aren't changing the experiment when I do it the first time versus the second time versus the 40th time. You know what I mean? So these are the things that we are trying to make sure don't change. Now, you will have a control group, okay? So if you see control here, we will oftentimes have a control group and should have a control group for any experiment that we set up if it's not just a survey. We should create a control group, which is something that we're going to use as a basis for comparing. It's the group that doesn't receive the treatment, that independent experimental variable. So if I were doing a plant, growing experiment, and I wanted to see if the plant was growing better with Coca-Cola, yeah, of course, versus water, just water, gross. I'm going to find out if the plants are growing, and so my control group is going to be the one that has the normal experimentation, the normal variables that we would expect. And so water is going to be like the plants that are receiving water would be the control group. The plants that are receiving the Coke would be the experimental group, okay? And my variable that I'm adding to it would be the Coke that I'm continuing to add to it, right? That might be, if I wanted to see how much Coke made it do better or worse, then I might be changing my amount of my Coke, and that's what I'm controlling. And so then my height or my livelihood of my plant might be changing based upon that. Okay, so that's a control group, and that's what's different. Control group is not the same as controlled variables. Controlled variables, all like temperature, everything is the same. Temperature, pressure, humidity, all that kind of stuff. Control group, I'm going to change one variable. I'm giving it Coke instead of water, okay? Well, the control would be the water. The Coke would be the experiment. All right, so why do we test just one variable at a time? What's important about that? Because we don't know what variable might be testing it. And this is why it's so hard to do experimentation with humans. And why, we might be, for instance, looking at this whole COVID thing and why people are dying. And we see all these crazy different symptoms. And we're like, is this a respiratory disease? Is this an an infection in the blood, right? Is it a circulatory disease? What's happening here? There's so many different things that are happening. Humans are so hard to do experiments on because there's so many variables that make a human tick. And so we try to identify one variable at a time, and oftentimes in human trials we can't. There's just too many variables, but we do the best we can. Outside of human trials, we can probably do a pretty good job. So why do we have the control? To see if there's a comparison, to have a comparison to see if there's a difference between the different groups. Why do we have constants? To get rid of other influences, okay, other variables that those influences might have. Did I say that right? Why do we perform multiple trials? And we want to confirm results. You might be surprised at how many trials are considered, valid. You might be, for instance, Mythbusters. I love Mythbusters, but watching those guys sometimes drives me crazy because they'll do the experiment one time and they're like, yeah, this is what happens. I'm like, no. In science, you typically, to do statistical analysis, you want to have at least 30 trials to say something conclusive, okay? Because, even flipping a quarter, right? You could flip a quarter 30 times, and it's possible that you could end up getting heads every single time. Now, that's not what's supposed to happen, but sometimes it does. And so on Mythbusters, they might do something, and they might be like, hey, look, I dropped the buttered toast, and it landed every single time, but they only do that test once. Well, actually, the buttered toast one, they did it a lot of times. That was good. I was proud of them for the buttered toast experiment. Anyway, so we want to make sure that we do it multiple times. 30 times is usually minimum. 5 times if you're, like, in kindergarten. All right, so we now know the scientific method. We have a good part of that here. We've got observing, formulating, hypothesis, and testing, the theorizing. So let's talk now about the difference between the theory and the law. What's happening there? So when we talk about a theory, we want to talk about why something's happening, okay? Modeling science is more than a physical object, okay? We have different models. You can think about the model of the solar system, the model of the atom, and things like that. It's not just a physical object. It's an explanation of how something works, right? Or how things are related. For instance, we use the model of the atom that Niels Bohr came up with that has a bunch of different rings, kind of like the parts of the solar system. And it's not an accurate model, but yet it helps us to understand something. And so it's good to have models that help us to explain how things work, even if they're not exactly correct all the time, okay? So we might have visual models, verbal models, mathematical models, and we already talked about an example there, but the theory, then we might use a model to help to describe what's happening with the theory. A theory is a broad generalization that explains a body of facts or phenomena. The big word you want to focus in on here is that it's explaining, okay? The theory is going to be telling you why. If you want to talk about the difference between law and theory, remember, theory is why, okay? Theory is doing an explanation of what's happening, that body of facts. So, for instance, collision theory. In chemistry, we have this idea, this theory that says that objects are colliding against each other, and that when they collide against each other, the atoms are bouncing off without losing energy, okay? So that's the collision theory, and it helps to describe things like the temperature and all sorts of great stuff. And so the collision theory is just one example of a type of theory. Now, it has to be observed over and over and over again. One of the misconceptions is that theories turns into law when you test it over and over again. No, a theory has been tested over and over and over again and shown to be true. Now, I won't tell you, though, that the theory never changes, because in science, theories and laws can both change. When you find new data and you have new information, as a scientist, change your mind, right? Oh, I was wrong. Again, remember, as scientists, we are not biased in that way. We are happy to be wrong. It's okay to be wrong. And so we were like, wow, what I thought before was incorrect. And now I know the truth because I've gathered new information. And now I'm going to change my mind because I was wrong before. Well, it's so great and so refreshing to be a scientist compared to a politician, right? Because in politics, if you change your mind, right, you're a flip-flopper, or you're going to lose your base, your constituency. It's sad, man. It'd be horrible to be a politician because you're not being the genuine human who can learn and grow, right? If you have to be playing the politics of it. As a scientist, you can be like, hey, I was wrong. I learned something new. Guess what? That's what growing up is. That's what getting wiser is all about. Taking in new information, learning something new. So yeah, it's cool to be a scientist. I love it. All right, let's continue on. Maybe. La, 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 la. Come on. There you go. All right, so that is theory. And again, talk about the laws now. The laws are the what. Remember, the theories are like the why, the laws are like the what. Okay, description of an observed phenomenon. Okay, often mathematical. A lot of times you're going to see a formula that's associated with laws. Think about the law of gravity. Oh yeah, Newton came up with this law with gravity, right? And so law is not the why, it's the what. Okay, it doesn't explain why, but yeah, we already did that. That's the explanation. It's a theory. It's a misconception that theories turn into laws with enough research. Okay, that is not the case. The laws are things like mathematical formulas. This one is force is equal to mass times acceleration, right? But it is the explanation of the phenomena. Whoa, sorry, I just got messed up there. The law is just basically describing what's happening versus the explanation of why it's happening. Okay, so that's the big difference there. Think about the evolutionary theory, right? That is an explanation of why creatures have gone from this to this, and how all of the different variety that we have on this planet exists, right? And so it's not a law; it's an explanation of why we think that all these different creatures exist in so much variety. The law, okay, if you think about gravity, the law of gravity, you're just trying to describe the what's happening. If I take a pen and I drop it, the why, I just broke my pen. The why is not part of what I'm explaining there. I'm just saying, hey, it drops at 9.8 meters per second squared. So the law would be the 9.8 meters per second squared. That whole idea about gravity, that's the what. The law can be shown to be true over and over and over again. That's the what. But the why might be trying to get into, what's happening behind gravity. Like, do we have a reason for why gravity is working? Things like that. Yeah, that's the difference. Okay. So let's go into your turn here. Identify which of the following is a scientific theory, hypothesis, and law. All right, hit the pause button. Boop, figure it out, and we're back. Two bodies in the universe attract each other with a certain force based on their masses and the distance between them. This sounds like a formula, doesn't it? Don't we have a formula? If you guys remember from physical science, that you have this law of gravity that talks about the masses, the m1, the m2, remember, divided by the distance squared, things like that. And then universal gravitational constants there. That's going to be a law, okay? If a pot full of water is watched while they're heating, the water will never boil, okay? Now, is this a hypothesis? Is it based upon observation? Is it something that you've heard, some prior data? Maybe you want to have it. Is it testable? Yeah. This all seems like it fits right into that hypothesis mode, right? Earth has a magnetic field because of a conducting fluid at its core. Again, a big part of theories a lot of times is that why. And so here's a because, trying to explain what it is. Now, is this testable? No, I'm not going to be able to test that per se. Not right now, maybe sometime in the future. This is a good explanation of why we think it might be working that way. Okay, so I'm going to let you pause on this one as well. Hit that pause button. This is a catalyst that is kind of fun to try to go through and explain. We want to try to identify the independent variable, the dependent variable, constant, and the control group. So quickly, we have this experiment. Oh, Bart, you're such a bad kid. And he decides to perform the experiment on 10 mice in a microwave for 10 seconds. Please don't try this at home. Mice do not deserve this. All right, he compared these mice to another group that had not been exposed. Okay, his test consisted of a heavy block of wood that blocked the food. He found that 8 out of 10 mice that were microwaved were able to push the block away. 7 of the non-microwave mice were able to do the same. Okay, so independent variable. What is it that he's controlling? What's the same, but then what's different, right? So if we look at the things that are the same, the number of mice are the same, the number of seconds are the same. There's one thing he's changed, the microwave. Some of the mice are in the microwave, some of the mice are not. That's his independent variable. The microwave radiation is his independent variable. That's the thing he's changing in each of these experiments. What's the dependent variable? Well, it's their ability to push, right? Are they stronger? Can they push the block out more? All right. So can the distance, or not the distance, but the number of mice that were able to get to the food, that's basically your dependent variable. The constant, well, he's gotten a few constants, right? He kept the number of mice the same. He kept the block the same size. He probably used the same microwave, right? The same amount of time. All those are constants. The control group, okay? So he had one group that was not exposed to the radiation, and that's going to be your control group, right? All right. So, ready to go on? I think we're ready to go on. Please? Please go on, please advance. La la la, you're killing me. There you go. Oh my goodness, it's just so annoying sometimes when your clicker doesn't click forward. Why did it go back so many times? What in the world is going on? Must need to reboot my computer or something. Okay, so that was our catalyst. And this is something else that I would want you to be able to do. And this is an exit ticket, but basically we're done with this lecture as soon as you do this stuff, right? Student conducts experiment to determine the effect of the amount of phosphorus and fertilizer in plant growth. Student's data summarized in the graph. Identify. Independent variable. What is it controlling? The time, okay, the number of days. What's the dependent variable? The growth, how much it's growing. That's what's going to be dependent upon how many days it's been going. The control group. All right, so what has he kept the same? Oh, he's got one of these the same that has not been changed, does not have any extra phosphorus put in it. So that's your no phosphorus or no fertilizer group, okay? And then constants, you know, what kind of things would it need to be constant? You know, the amount of light would need to be constant, temperature, amount of water they're getting, all that kind of stuff, right? All right, so that covers what we want to talk about. There's a little zoomed in picture of that graph. Yeah, so hopefully this was fun. I enjoyed this lecture. I hope you did too. The big thing about this is that science is something that we get to interact with on a day-to-day basis, and the scientific method is a great tool to help us try to discover the truth about the world, to solve the problems. Remember that scientists are humans like anybody else, but we want to try to make sure that we're, as scientists, avoiding bias, being as objective as possible, collecting the data and seeing what that data is determining without using, without having our political whims and things like that affecting us. And without having our preconceived notions affecting us. It's important to try to be as objective as possible as you get into the world of science. And I'm excited to have some of you guys get into the world of science and become those great scientists that are going to find some truth for us and help us to have a better world. So have an awesome day. Thank you for listening.